Hey guys, welcome back to another video. So today is going to be part two of the two-part video series that I said I was going to make. I realized that the last time I posted a video on this subject matter was 3 months ago, and I apologize for that. This semester in uni has been pretty hectic and pretty busy for me, but I thought today I finally have some time to record the second part of this video. So in the previous video, we left off at arithmetic progressions, or APs, and this video we are going to cover the remaining two progressions, namely the geometric progressions, or also known as GP, and the arithmetico-geometric progression. Arithmetico-geometric progression, also known as the AGP. Now, I thought this was going to be the only two topics that I would cover, but I've decided to cover the third topic, which is somewhat related to the progressions, and that is the means of a progression. We're going to focus on two means. We're going to focus on the arithmetic mean and the geometric mean, right? And then we will cap off with a statement on what's known as the AMGN inequality, which is one of the most important inequalities in all of math. All right, and then maybe if we have time, I'll go through some bonus stuff. Now, this one is not guaranteed, but if we have time, we will go through some bonus stuff, which you'll see if we have time to talk about it. So let's start with the geometric one. So the geometric series is essentially like an arithmetic progression, except the only difference is in an arithmetic progression, if you recall, let's recall what an arithmetic progression is. An arithmetic progression is essentially a sequence of terms where each subsequent term is a constant sum over the previous term. So this right here is our bog standard example of a arithmetic progression. So you can see that each subsequent term is a constant d added onto it, right? And this d can either be positive or negative. So it can be a constant decrease or a constant increase, right? So this is what an arithmetic progression is. And we recall that the nth term was a plus n minus 1d, and that the sum of the first n terms, which you spend most of the video doing, is t1 plus tn, also equal to, if we were to plug these two formulas with herein, it would be 2a plus n minus 1d. If you want to see how these formulas are derived, you can go back to part one of this video to look at the full arithmetic progression breakdown. So what a GP is it's similar, but instead of having the terms be a constant increase in sum, we are going to have the terms be a constant increase in product. So every subsequent term is an increase by multiplying the previous term by a certain constant. So this constant, we refer to it as R. So as you can see here, this is a box standard example of a geometric progression. Every subsequent term is an R factor bigger than the previous term. You can see the parallels between the arithmetic and the geometric progression, where in an arithmetic progression, each term increases by d and its sum by d. In this one, each one increases by r, but it's by a factor of r. So we keep multiplying a constant r onto the previous term, right? And this one goes on forever. So much like how in our arithmetic progression, d here was known as the common difference. Common difference. All right. In the geometric progressions, everything remains the same. A still represents the first term. Tn represents the nth term. Sn means the sum of the first n terms. The only difference in a GP is that in a GP, this R here is known as the common, not difference, but common ratio. Right? So the ratio here just refers to the fact that if we divide AR by A, we get R. If we divide AR squared by AR, we get R. So essentially, each term is increased by a factor of R, right? So that's our common ratio. So obviously, when we talk about GPs and we talk about progressions, we want to talk about the first n terms of the progression, namely what is the Tn, or the nth term, what is the sum of the first n terms. But in this case, GPs actually have a special add-on, which we will get into later. So let's talk about the simplest thing. What's the nth term? Well, we can do this by pattern observation. If the first term is starting with A with no r's, we can see that each term here increases by a factor of r. So if we label the first term as T1 and everything as T2, T3, and T4, and so on, to represent second, third, fourth, fifth, and so on, we notice that there is a parallel between the number of the term and the number of the power. Namely, that the power is always going to be 1 less than the actual term number. So we can deduce from this that Tn is going to be equal to A, because if you notice, every single one of them has a factor of A, because obviously you don't want to forget the first term, because the first term is how you start building the progression. And then we're going to multiply it by some factor of r. But what power of r? Well, r here is always going to have a power that's 1 less than the actual term number. So this is going to be equal to n minus 1, because we're going to have 1 less than the actual term number. And this is actually all there is to the formula for the nth term in a geometric progression. And this works for n that is at least 1. Remember that there is no 0th term here, because if it was a 0th term, we had a over r, which would imply that we are going backwards in terms of the progression. Instead of multiplying by r, we're dividing by r. And in fact, you can actually extend this, just like the arithmetic progression, you can extend this both ways. If you extend this the other way, it could be just minus d, minus 2d, minus 3d, and so on, all the way to the left side. This one, you could just divide by r infinitely in the other direction. But obviously, we're thinking in the forward direction like this. Okay, so this is pretty simple. It's just the first n terms. Now, when it comes to the sum of the first n terms, however, sum of the first n terms, this one is a bit, well, let's just say it's easier. But the formula for how to come up with it is a bit more difficult. Because if you recall, we spent most of the previous video looking at how to derive the formula for the sum of the first n terms of an arithmetic progression as credited to, I believe, Gauss, because it was called the rainbow sequence. That was how he came up with it. So the way we come up with the sum of the first n terms is we're going to do some cheeky manipulations. So what are we going to do? Well, we're going to let s of n be equal to the sum of the first n terms. So it's going to be a plus ar plus ar squared plus all the way to the nth term, which we already know what it is based on our formula. It's going to be equal to ar n minus 1. All right. Now, this is what we are looking for. So what are we going to do here? Well, let's do some cheeky manipulations. Because this is a finite sequence of terms and it's a finite sum, it's going to not be an infinity. So that means that we can do whatever we want to the sequence, aka multiply stuff to it and rearrange so that we can get a nice number, right? And remember, rearrangements are only allowed for finite terms. Finite, right? Either they are finite or they're convergent, right? And I'm going to define what convergent means later, because this is actually very important for the context of geometric progressions. This is where the first time you're going to see this word convergent, right? So what we're going to do is we're going to multiply this entire sum by r. And you're going to see why we're going to do that. If we multiply this whole sum by r, we're essentially going to be distributing r across basically all of these terms, right? So we're going to FOIL out and basically multiply all of these terms by r. So what this is going to be equal to is a times r is ar times r is ar squared times ar is ar cubed, and so on, all the way up to the last term, where ar n minus 1 times r is ar to the power n. So this is going to be equal to r times the sum. Now, why did we do this? Well, we're going to take this first equation, which was the original sum we're looking for, and this second modified equation, where we multiplied it by r, and we're going to subtract the two equations. So we're going to subtract the two equations. It means that the left-hand sides of both equations will be subtracted, and the right-hand sides of both equations will be subtracted. So when we subtract the left-hand sides, we're going to get s of n minus r times s of n And this is going to be equal to a plus ar squared plus dot 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 plus arn minus 1. This whole thing we are going to subtract off from the modified equation. Actually, wait, I'm going to write this in a specific way because you're going to see what we're going to do with this. ar plus ar squared plus dot 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 plus ar. I'm going to put n minus 1 plus arn because n minus 1 is in this sequence. It's just one term before it. It's just we didn't write it out. Now, why did I write it this way? Well, the left-hand side is going to be pretty simple. We can factorize s of n out to get 1 minus r times s of n. This is just the factorization of this. Now, what this is going to look like? Well, we are subtracting a bunch of terms from a bunch of terms. And if we notice, all of these terms overlap with all of these terms here. So we're essentially taking all of these terms, subtracting them from themselves. Because it's going to be because if we expand this minus out, we're going to get minus ar squared minus ar cubed all the way up to minus ar to the power of n minus 1 minus ar to the power of n. So we're going to have all these terms that we're going to subtract away from each other. So all of these terms, let me switch color here, are actually going to get canceled out. All right, everything here is going to be canceled out. So what we're going to be left with is we're actually going to be left with just a, because a isn't subtracted off from anything. All of these terms cancel out, and we're left with minus, because we expanded this negative into this bracket, ar to the power n, because this one also doesn't have anything that it cancels out with. Everything else cancels out. So we're left with this formula right here. Now, if you look, Sn here is actually what we're looking for. So we are going to actually divide over 1 minus r to put at the bottom, and then clean this up by factorizing a out to get a to the power, a times 1 minus r to the power n over 1 minus r. And this is, in fact, our formula for the sum of the first n terms. Now, there are conditions. Okay, there are conditions that we must follow. Actually, there's only one condition. R here cannot be equal to 1. And I think you can see why. Because if R here is equal to 1, that means that the denominator is going to be 0. That's not fair. Because if we divide by 0, we're going to get something. Oh, God. Apologies there. If we were to divide by 0, we'd have problems. Because that's infinity. And I think you can see the reason why r cannot be equal to 1. If r was equal to 1, that means that our geometric sequence, our geometric progression, is going to be a times r is a times r squared is a times r cubed. We're going to have a's, just all a's. So when r is equal to 1, we're essentially just going to have a sequence of constant a's, n constant a's actually. So they're going to be n a's. So therefore, the sum of this is just going to be equal to n times a, right? Which has nothing to do with this, right? And you'll see importantly why r cannot be equal to 1 for a more important case, right? So this formula specifically says that r cannot be equal to 1. Another thing, which is interesting, is that for certain cases, we don't want r to be minus 1 either, but not for this one. For this one, r being minus 1 is perfectly fine. All right, r is actually perfectly fine that r is equal to minus 1 because that means that we're just going to have the sign of the terms alternate. We're just going to have a minus a minus a minus a because it's going to be r. It's going to be negative 1 to the power 1 and then negative 1 squared and then negative 1 cubed. It's just going to alternate between positive and negative. So it's just going to end up being we're either going to have a 0 where all the a and minus a cancel out, or we're going to have an a. So only either one of these sums is possible, basically. Only one of these things is possible. So that's not a really interesting sequence, but because we're not dividing by 0, r equals minus 1 is a perfectly valid option. Now, this is fair enough. And if you notice, r can either be negative, and it can also be positive, right? Because if it's negative, we're going to get some negative number. If r is negative, then that's fine. We're just going to get a negative sum, right? Because that means that we're just going to have a bigger and bigger amount of negatives that just keep alternating. So, for example, let's say our term started with 1. And let's say that our r here was minus 2. Okay, so this is an example. We started with 1. Multiplying 1 by minus 2 gives us minus 2. Then minus 2 times minus 2 is 4. 4 times minus 2 is minus 8. Minus 8 times minus 2 is 16. So if you notice, this is just an alternating sequence of the powers of 2. So what it's going to look like if we were to sketch out what the graph of this thing is going to look like is we're starting at 1. We're going down to minus 2, going up to minus 4, going down to minus 8. If you notice, okay, I think the graph is a bit small. We're starting here, and then going down here, and then going up higher, then going down lower, then going up higher. It's basically just going to keep growing, right? So if you know, so you can say that this this sequence right here is just growing really, really like drastically. It's just going to keep growing at this point, right? In fact, we can say it's growing exponentially because it's growing by a power of 2 each time, right? So that's the general look of what this graph looks like. Now, what I'm about to do is we're going to go into the third and final part of geometric progressions. And this is actually the most important part because here is where we get into some series theory. Now, this topic is not only important for algebra, but it's also important for those of you who are looking at this and looking to study calculus in the future. Because this is where we're going to actually use a bit of calculus to talk about what's called S infinity. Now, what exactly is S infinity? Well, S of n was the sum of the first n terms. Well, S of infinity is the sum of infinitely many terms. Now, I know what you must be thinking. Is that even possible, right? If you've never encountered progressions before, you might be thinking, is S infinity even possible? Because if we think about it with an arithmetic progression, if we were to try and sum this to infinity, we'd probably end up with, if we were to add all of these together, right? It's not common actually. If we were to add all of these things together, right, infinitely many, right? Instead of stopping at some n, like we did here, we stopped at some n. If we were to go on forever, you would safely get infinity, right? And I'm going to justify here why it's the case. And this is where we actually need to get into some terminology before we talk about what does it mean for some sum to have an infinite sum. All right, so let's talk about what convergent and divergent means. So convergent and divergent are two very important terminologies in sequence theory and series theory. And I referred to this at the top here, rearrangements for only finite or convergent sequences. Now, what does it mean for a series to converge? Well, a series converges if you can actually find some number, right, in layman's terms. A series is convergent if it actually has a finite value, right? So a sequence and a series have different meanings for convergences. For a sequence or progression, which is what we're calling it for this chapter, a progression is convergent if the terms in this progression approach some number. So if we look at a simple progression like this, 1, 0.99, 0.98, 0.97, and then go on, and then we get to 0.01, 0.005, 0.001, and then 0.0005. If you notice, this progression is unending, but it's clearly going somewhere, right? It's clearly going somewhere, and that somewhere most likely means we're eventually going to reach 0. But we're not saying that it's going to eventually reach 0 because this series is going to go on forever. But if you notice, we are just decreasing by 5, then 1, then 5, then 1. It's just we're just going to keep adding arbitrarily many zeros at the end of this, behind this point until we eventually reach 0. It's getting really, really close to 0. So what we say in a situation like this is that this progression converges to 0. It means that the terms in this progression are going to basically, they're going to 0, but they're not reaching 0. Right? Remember, converging means it's reaching 0. It's not at or getting to exactly 0. It just means that it's going to 0. Right? That's very important. Another example, which is a more famous example, because this one is not really like a arithmetic or geometric progression, actually there's no format to this one, is this progression. We start with 1, then we divide 1 by half, then we divide half by half, we divide a quarter by half, we divide an eighth by half, and so on. And then we let this continue on forever. This is a geometric progression because we can see that each term is getting multiplied by a half. Right? Essentially, we are dividing by 2 here, but dividing by 2 is basically multiplying by half, and every single term here is multiplying by a half. Right? Now, if we were to look at the decimal expansions of each of these terms, right, you will see that we're starting with 1, and then we're going to 0.5, then we're going to 0.25, then we're going to 0.125, then we're going to 0.0625, and then going on forever, right? These numbers are going to get smaller and smaller and smaller, and also get closer and closer to 0. But will it ever reach 0? Well, for this one, technically no, because there's not going to be any number that when you multiply it by half, you get 0 aside from 0 itself. But because none of these terms are 0, this sequence never actually reaches 0, right? If you notice, because the numbers are essentially, we're going to get smaller and smaller and smaller and smaller and smaller, and getting closer and closer and closer to 0, but we never actually reach 0. Like if we were to do like a visual sketch of what this progression looks like, all right? So if this starts at 1, what happens is that the terms will get smaller and smaller and smaller, and they're going to slowly get to 0, right? This is 0 right here. They're going to slowly get to 0, but they will never actually reach 0. They're going to get very close, but they never actually reach 0, right? This right here is what we call convergent, right? This is a proper definition of what we call convergent, because these terms are getting very, 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 very close to 0, but they never actually reach 0, because there's no way for them to actually reach 0. Same thing for this one. If we just started from here, right? If we ignored the front part, we just started from here, where we just go 1, 5, 1, 5, and then we follow this pattern of adding an extra 0 every 2 terms. These will also get really, really close to 0. In fact, this visualization of this is just going to be like 0.01. We're also going to get really, 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 really close to 0 because we're getting smaller and smaller each time, but we will never actually reach 0 because we're just going to keep adding a 0 each time with a number at the back, so it's never going to be actually equal to 0. So that's the definition of what a convergent progression is. All right, so a convergent progression is simply a sequence of numbers that get really, really close to a certain number, but they never reach there. In proper mathematical terms, we say that a sequence is convergent, or a progression is convergent. All right, so we say that this progression T1, T2, T3, and so on, all the way up to Tn, and then Tn plus 1, and then Tn plus 2, and then going on forever, we say that this sequence, so let's say I call this sequence S, this sequence is convergent if the limit as n approaches infinity of Tn exists. So let me explain what this term here means. The limit as n approaches infinity of Tn, what does this mean? Well, a limit is essentially a mathematical it's like a mathematical function or an expression to express when something is getting really, really close to something. So when n approaches infinity in this case means that n is getting arbitrarily big, right? So n could be going to like T100 or T200 or T500 or T1000, even a million or something. T1,000,000. You see I'm using words right now. T10 to the power of 10 to the power and so on, right? The number of the term is getting ridiculously big at this point. So we can say that it's approaching infinity because it's getting really, really big. So it's basically going to like infinity. What this means, the limit as n approaches infinity of t to the n, or t of n, is that as this term number gets arbitrarily big, means this as the sequence gets arbitrarily far along, right? It's getting really, really close to some number. Meaning that you can see by like the 100th or 500th term that you can see that the terms are getting super, super close to some number. Right? A perfect example of this would be this one. Because in the case of a number like in the case of this sequence, we are getting closer and closer to 0 because every single time we are multiplying by half. So we're dividing these decimals by half each time, and we're getting smaller and smaller and smaller each time. And you can see that these numbers, if you type into a calculator, just keep dividing these by 2, you can see that they're getting really, really close to 0. Right? So what we say here, for this sequence in particular, is that the limit as n approaches infinity of t to the n is equal to 0. All right? So that's what it means. It means that as the term gets as the term number here gets arbitrarily big, as the sequence goes far off into infinity, it gets even more closer to 0. So the limit here as n approaches infinity means we're looking at what does the sequence approach? What number is the sequence approaching? And in this case, the progression here, the term is approaching 0. So we say that the limit is 0, meaning that it can only go to 0 and nothing beyond 0. Right? 0 is the final, it's basically the final destination. We can also define limit as n approaches infinity as like a final destination that cannot be reached. Right? Because remember, when we say that a limit exists, when we say as the limit as n approaches infinity, we're never saying that n reaches infinity. Well, because infinity by itself is not a number. We're not describing saying infinity is a number. We can't count infinity. Well, technically we could, but we're not saying that infinity by itself is a number. When we say what a limit is, a limit looks only at what it approaches. It never specifically states what happens when we get to that point. So let's say we said limit as n approaches 50 or something. What this means of limit n approaches 50 of whatever, some function of n, what we are looking at is what happens to this function as n goes to 50. So maybe when n goes to 45, n goes to 45, then 48, then 49, then 49.5, then 49.75, then 49.9, and so on, right? This means that it's getting really, really, really close to 50, but we never actually reach 50, right? The limit here doesn't need the point or whatever we are evaluating to specifically exist at the number it's approaching, right? So even though it's getting really, really close to 50, we don't necessarily care about what happens at 50, right? So n here is getting really, really close to 50, but it doesn't actually matter whether or not n equals 50 even exists, or whether or not it even exists at n equals 50. We just want to know what happens as it gets closer to 50. So in this case, we don't really care what happens when n reaches infinity. We don't really care what happens when it reaches the end of the line because, well, there is no end of the line here. But what we do know is that it's getting really, really close to 0. So we don't really care if it will ever reach 0 or what happens if it actually reaches infinity. Well, we'll never reach infinity. But we don't really care about what happens further down the line. We just care that it's getting close to 0. So the limit, or essentially where it can go, the final destination here, is 0. But you will never actually reach 0, right? Reaching 0 is a different story. But a limit just says that it is approaching that destination, but you will never reach it. Right? A famous example of illustrating this is what's called Zeno's paradox, I think, where a runner, to run like a 1 meter race, he first runs half of it, so 0.5. He then runs half of the remaining, so 0.25. And then he runs half of the remaining, and then which is 0.125, and then keeps running half of the remaining, half of the remaining, half of the remaining, until eventually he should be able to finish the 1 meter race. But theoretically, or philosophically, or like theoretically, because he's never actually reaching the end, because he keeps running half of the remaining distance, what we say here, in this case, is that he is getting really, really close. Really, really close to finishing that 1 meter race, or running that 1 meter distance, but he would never reach it. But never reaches. Right? It's getting super, super close to finishing that 1 meter race or that 1 meter run, but he never reaches that 1 meter because he's always running halfway. He's always only accomplishing half of the distance. So what we say here, what we can say, is that he will only finish that meter-long distance after an infinite number of steps, right? He will never be able to finish it. After an infinite number of half, he'll reach. But because an infinite steps is infinite, it will never end, he will never finish the race. Only after he completes all infinite of those steps will he complete that 1 meter race, right? And I know this is a bit difficult to grasp for some people. Is that how is it possible that he only finishes after an infinite number of steps while he would never probably finish it? Because if you think about it, if he were having a finite number of steps, the distance he completed is still less than 1. There's still a bit more that he has to complete half of, then half of, then half of. All that being said, all of that is going to contribute to getting closer and closer and closer to 1, but never reaching. So we say that the limit of the distance, right? The limit of the distance. So let's say we call dn the number of steps he's taking. We say that the limit as n approaches infinity. So the distance he is approaching, the distance he will accomplish after an infinite number of steps is 1. Because it will take literally a never-ending amount of steps for him to eventually reach 1. He would never reach 1, but after an infinite number of steps, he'll reach 1. So that's the basic concept. I think it took quite a while to explain what a convergent progression is. Right? It's just getting really, really, really close to it. Now, as for series-wise, for a series, convergent basically just means the sum approaches something. So it just means that for a convergent series is a series where the sum actually is some number. We say that a series is not convergent if it approaches infinity, or essentially if it is at infinity, right? So if the series actually reaches infinity, then we say that it is a divergent series. All right, so that's actually the opposite. Divergent, in this case, divergent is the opposite of convergent. That means that instead of approaching some number, it gets arbitrarily big to the point where it never actually reaches anywhere. So for example, a simple one is the geometric progression 1, 2, 4, 8, 16, and so on. If we just keep multiplying by 2 here, because every subsequent term is multiplied by 2, we're going to get to a point where the number gets so big, it's going to be 2 to the power of something. It's going to get so big that it blows up to infinity. What we say it blows up to infinity. So because it never actually approaches anything, we can actually see what the graph looks like. The number literally just explodes. It literally goes up to nowhere. It just goes up and up and up forever. If it doesn't approach anything other than infinity, we say that the progression here is divergent. Well, the series is divergent if it doesn't actually approach anything, if the sum of the series doesn't actually approach anything. So that was quite a long tangent on how to explain divergence. So how do we actually deal with the concept of S infinity now? All right, so I'm going to have to actually move over this way because it's going to be way easier to explain S infinity. So what's S infinity? S infinity here means we're going to sum up every single possible term in some arithmetic progression, sum of infinitely many terms, all right? And we're going to try and see if we can make sense of what this means. So we know that the sum of the first n terms is going to be 1 minus r power n times over 1 minus r. This is the formula that we derived just now for the sum of n terms. Well, we're going to see what happens when we try and make this n go to infinity. So in other words, what happens when n goes to infinity? Where instead of summing a finite number of terms, aka n terms, we try to sum up everything in the progression. Well, we can't say everything because there are an infinite number of terms, but what happens when we try to sum literally every possible term in this progression? Well, we're going to have to see predominantly what happens to this term, because it's the only term that n is present. Everything else is just a constant. So what happens to r power n? Right? Because everything else is a constant, it's not going to be affected by n. So if n goes to infinity, what happens to r power n? Well, we can actually narrow this down to a few circumstances. So first off, let's look at what happens when r is bigger than 1. Because if r is bigger than 1, that means that this number is going to grow like this. So for example, let's say 1.5 to the power n. This number, if we keep making n bigger and bigger and bigger, this number is going to grow like this. Or let's take 3 to the power n, meaning that we are taking 3 and multiplying 3 by itself n times. And if we make n arbitrarily big, or if we make n super large, like 3 to the 100, this is a huge number. So that means that this blows up to infinity. This is going to approach infinity. So what we can say is that when r is greater than 1, r to the power n basically goes to infinity, if n goes to infinity, right? So that means that from what we just talked about this now, this sum is going to be divergent. Why? Because r to the power n here is in the numerator, and we're going to have an infinite number here, basically, because a times 1 minus r power n is basically going to be infinite, because this number is going to be so huge that it dominates over the other terms, and it's just going to be infinite. And it's going to be infinity divided by a constant, which is infinity. It's just going to be so big that it blows up. So case 1, when r is greater than 1, it's divergent. We don't care, right? Because that means that the sum to infinity, it's infinity. It doesn't matter. It's not important to us, right? It doesn't really do anything because it's an infinite sum that goes to infinity. Not interesting. The same here actually goes for r less than negative 1. Because that means that the term is going to go, that means that the sum, or at least the term itself, is going to look like this. It's going to start off with a positive number, then go down to a negative number, then go up and down and up and down and like that, right? Much like what we saw with this one right here, where it keeps going up and down, but you see an overall trend of it increasing, and it doesn't seem like it's approaching anything. Right? In this case, we say that the sum is also divergent, or in this case, r power n doesn't exist. It doesn't exist. When n approaches infinity, this thing basically, it's divergent. Right? Well, it's wrong to say that it doesn't exist. R power n is just, it doesn't approach anything. It's not that it doesn't exist, it doesn't approach anything. Right? Because the wave is growing so big that the overall amplitude of the wave is getting larger and larger and larger, and it's not really converging or approaching anything, right? So it doesn't approach anything. So we say that this is still divergent, right? So that's the case when r is less than negative 1, because, for example, if r was negative 2, we saw just now, it would be 1, then negative 2, then 4, then negative 8, then 16, and so on. The number itself is getting bigger and bigger and bigger, and it's going negative, positive. So the magnitude itself keeps growing like a lot. So we say that it never approaches anything, so it's just divergent. Okay. Now r itself can't equal 1 or negative 1. Well, r equals 1, we already know it can't happen, because if r equals 1 did happen, we would be divided by 0, so we can't do that. And of course, if r equals to 1, we would have a forever. And summing an infinite number of constants is obviously just going to give us infinity, because it's basically an infinite number of constants summed together, which is just, the number is just going to keep growing. And in fact, it's growing linearly, right? Because we are taking the number and adding it to itself over and over again for an infinite number of times. So yeah, so it's going to be an a, then 2a, then 3a, then 4a, then 5a. It's just going to grow to infinity times a, which is just infinity, because it's, yeah, a times infinity is just infinity, because the number is so, because we're adding a to itself so many times that it becomes super huge. If r is negative 1, that becomes an even bigger problem, because if we try to sum this to infinity, the terms look like this, right? It's not growing, right? For one, it's not growing because the value itself doesn't change. It gets to a, negative a, negative a, negative a, negative a, and forever, right? So it keeps alternating between a and negative a. So it stays stagnant, but we can't say it's convergent either. It's not convergent because it's not approaching anything. It just keeps alternating between two values without even deciding on what number it's going to reach. Is it going to reach a? Well, the next term is going to be negative a. Well, is it going to reach negative a? Well, the next term is going to reach a. So it's never going to actually reach anything because it keeps alternating between these two values. So what we say here is that Rn doesn't approach anything either, right? It doesn't approach anything either. So we say that it's divergent because it's not convergent. It doesn't converge to anything because it doesn't approach any number. It keeps hopping back and forth between a and negative a and never really reaches a conclusion on what number it wants to be, or it can't decide what number it wants to be. So we say that it is, there's a problem, basically. So it doesn't approach anything, therefore it's divergent. Now we move on to the last and final case because we've nullified, let's look at the number line. We have -1 and 1. So we've nullified this side. R less than -1 is a problem. R1 is a problem. And these two themselves are problems. So we're left with this side where R is between -1 and 1. All right, so let's see what happens in this range. If R is between 0 and 1, so we say it's positive, that means that we're going to have something like 0.5 to the power n, right? Because we're looking, again, at R to the power n, right? So if you think about it, if we are multiplying a decimal by itself, you can try this on your calculator, or if you have anything that calculates, try and make this n for 0.5 bigger and bigger and bigger. You can see when you're multiplying 0.5 by itself, the number gets smaller because you're having 0.5 each time. So 0.5 times 0.5 is just half of 0.5, which is 0.25. Half of this is 0.125. Half of this is 0.625, and so on. So this one actually goes to 0. As you previously saw, this one is actually going to 0. So when R, and in fact, this is not just 0.5, it can work for any number between 0 and 1. So what we can say is that when R is between 0 and 1, this one actually gets closer and closer and closer to 0. Right? It gets closer and closer and closer to 0 if R is between 0 and 1. This is the case when this is what happens to R power n. Right? This is n, and then this is R. Right? So as n gets bigger and bigger and bigger, it gets closer and closer to 0 because it's shrinking. So in fact, this is convergent. Right? And the same thing actually can happen with -1 and 0. Well, you might be thinking, well, is a negative going to alternate? Well, as it alternates, if you think about it, if R is between 0 and -1, the value itself is going to shrink. But it's just going to alternate between positive and negative and positive and negative. So it's going to start here and it's going to go down here, but it's going to rise back up but never reach the actual original. It's going to be a bit less, then it's going to drop down, but it's never going to be as drastic as the previous. Right? So if we were to sketch from the top, it will be like this, but then it won't go down as much, then it won't go up as much, then it won't go down as much, and then up and down. So it's just going to be, this wave starts to mellow out, essentially, until eventually it should get somewhere. All right. So if you notice, this graph, instead of expanding ridiculously like what we're seeing here, it's shrinking. The wave itself, because the numbers are the magnitude itself is getting smaller and smaller, it alternates, but it's getting closer and closer and closer to 0. It's hopping back and forth, but it's hitting this like ceiling really quickly where it's like it's growing slower and it's shrinking slower. So it's getting really, really close to 0. We can say that this wave is damping. So in fact, this one is actually also convergent. Right? So in other words, we can say that if it is between 0 and R is between -1 and 1. Well, actually, we haven't considered R equals 0 yet. But if R equals 0, then we're just going to get A, 0, 0, 0, and forever, because multiplying A by 0 is just going to give us 0 forever, which obviously is going to converge because it's an infinite number of zeros, which sum to 0. So the sum of this is just going to be A, which is trivial. So R equals 0 is, in fact, also convergent. Trivially convergent because, every other term but the first one is 0. So we say that in general, if R is between -1 and 1, it's convergent. All right? Or in this case, R power n is convergent. So what does that mean? So let's look back at our sum of n terms formula. Okay? So we know for a fact now that if R is between -1 and 1, R of n is convergent. But what exactly does it converge to? Well, we can see that from what we've seen, r power n gets to 0 because it's getting closer and closer, either like this to 0, or it's hopping up and down before it eventually reaches 0. So if r is between -1 and 1, r of n actually goes to 0 as n approaches infinity. Okay? So let's define S of infinity like this. Let's say that the sum of an infinite number of terms is going to be the limit as n approaches infinity of our original sum of n terms. Because this describes a finite sum of n terms, but if we want to describe an infinite sum where we try to sum every term in the series, we're going to need to let n go to infinity. Right? We're going to need to have the sum, or the number of terms we adding to the sum, get more and more and more and more and more until it eventually reaches an infinite number of terms that we're summing together. Now, this is going to be the limit as n approaches infinity of our formula. Right? Now, the only thing that's going to be affected is this r power n term. And we know for a fact that as n approaches infinity, r power n goes to 0. So eventually, we can just say, well, the limit as n approaches infinity of r power n is 0. So therefore, this term just disappears and becomes 0. All right. When we evaluate this limit, this goes to 0. So therefore, this overall sum here is 0. Overall sum here, this part is 0. Right? So we just replace this by 0 and get rid of the limit because that's evaluating the limit. This means that we have this sum remaining, or this formula remaining. Well, 1 minus 0 is just 1. So we're going to have 1 times a, and we are left with this formula. Now, this is what we call the sum to infinity of a geometric progression. And it only works for geometric progressions because arithmetic progressions can't shrink a number, or it can't converge, because an arithmetic progression keeps adding a certain amount. So it's either going to grow like this or grow like this. If d is positive, then the number is going to get bigger and bigger and bigger. And then if it's negative, it's going to get smaller and smaller and smaller, but it's still going to diverge. It would never reach anything. So this, in fact, this is a sum that is unique only to geometric and, as we'll see later, AGPs. Now, this is a conditional because this is not always the case. This is not always true. There is a very specific condition for a sum to infinity. As we've established, not every value of r is going to make this r power n go to infinity. If it's greater than 1, less than -1, or equal to 1 or -1, we're going to run into problems. They're all going to be divergent. So in fact, this formula only applies if r is between -1 and 1, or sometimes, or usually, if we want to be fancy about it, we said that the absolute value of r is less than 1. All right? So a more complete definition of the sum to infinity of a geometric progression is that it's equal to the first term divided by 1 minus the ratio, and given that the absolute value of r is less than 1. All right, so this is the more complete definition. So in fact, we can actually say what the sum of half plus a quarter plus an eighth plus a 16th. So this one is like our good old, running a 1 meter track and seeing whether or not he will actually reach 1. This is, we can evaluate this and see if it actually is equal to 1, eventually reach 1. We can see if this is actually true by using the sum to infinity formula. Well, the sum to infinity formula is going to be the first term. The first term of this progression is 1/2. As we can see, the ratio here, each term is going to multiply by 1/2, and 1/2 is less than 1. The absolute value of 1/2 is less than 1, so we can plug the formula in. So it's going to get 1/2 over 1 minus 1/2 is 1/2, so 1/2 divided by 1/2 is 1. So therefore, the infinite sum of all of these like 1 over 2 power n's is equal to 1. So after an infinite number of steps, he does eventually finish the race. But a finite number of steps, he's never going to finish the race. All right, so that is the proper definition of what an infinite sum of a geometric progression is.